So today I will present a recent work. It sound what the title is Frobenius quotients, inflation categories, and the weighted projective line. So first of all, I will start with a motivation. So let's start with motivation. So this goes back to the so-called the Birkhoff problem. Birkhoff problem. So this is maybe 90 years ago. So let's fix n at least two. So the so-called Birkhoff problem, the aim is to classify the indecomposable, so indecomposable in certain category, indecomposable pairs. So which are given by A comma B. So well, with this B is a building group such that this is annihilated by P to the power n. So where P is the prime, A is the prime. Sorry. So it's P is the prime. And A is a subgroup of this B. So now that we know that this actually the B is the module of some of the residue ring of Z modulo P to the power n, and B is just a submodule. So so Birkhoff wants to count this kind of indecomposable pairs. How many are they? So it turns out that the numbers, such indecomposable pairs are finite. So the number is finite, even only if this n is at the most 5. If n is 6, then you have infinite many such indecomposable pairs after isomorphism. So this is so-called a Birkhoff problem. And that kind of compared with that is more recently, then this is the so-called Birkhoff type problem. So as we see that actually this A and B are modules over some Artinian rings. So that's the Z modulo P to power the ideal generated by to the Pn. So then somehow the analog of this ring. So this studied by Daniel Simpson. No, 2007. Then later more intensively by Ringel and Schmidmeier. Around same time, I think. Yes. So for this, they started quite a similar problem. So this K is a field. Then they consider this Sn. So this is so called they call this the submodule category. So by definition, this category, the objects just a pair of, so it's a submodule. So so this xi is just the modules over the truncated polynomial algebra, and then S1 is just a submodule of S2. But more slightly more generally, you can say that there's a homomorphism from X1 to X2. So this actually, anyway, this is the objects. And the morphism is just given by a commuter diagram. So a morphism. So this is assume this is an object. Then this is another object. So then this is one morphism. This is another morphism. Then this commutes. So this should be viewed as a morphism. So then then they want to classify the indecomposable objects in this category. So you will see that it's easy to see that this guy is a subcategory of a certain module category. Then we have similar answer to this finiteness problem. So we have this submodule category is representation finite, meaning that have only finite many incomposable objects. If only if the same answer, this n is at the most 5. And moreover, so the main contribution of Ringel and Schmidmeier, we want classify indecomposable objects in this category when for n equals to 6. And in that study, they use the covering theory, and on the covering case, I will also mention that in the covering category, they use the representation theory of the tubular algebras in the sense of Ringel. Yes. For our talk, I'd like to mention that this category Sn is of Frobenius exact category. So so certainly it has a natural sorted sequence, and it becomes exact category of Qiang. And by Frobenius, we mean that projective are same as injective. For example, this projective injective objects in this category is quite easy to classify. So this is incomposable projective injective objects. Another one is also quite trivial. Yeah, this is identity. Yeah, so this is we have these two incomposable projective and injective. Let's give an example. So let's consider n equal 2 case. This is the simplest case. So one can draw really AR equivalence. It turns out that this Sn, the category submodule category has internal AR sequence and then AR equivalent. And for this guy, it's quite easy to draw. You can actually quite easy to classify all the objects there. So yes, let's draw a little bit. So this is certainly this K is a trivial module. Let's set A to be this truncated polynomial algebra, this two-dimensional ones. Yes. Then this we have AR equivalent. So in the middle, this is the projective ones. So this is yes. So this is this is the AR sequence, and then this guy, yes. This is also a sequence because the K is embedded in A. And yes, this is another projective. Yeah, this identity, sorry. Yeah. So we have to identify this with this. We have to identify this. And you see that the indecomposables in this category is the number is 5. So we have two projective and injective, and then the three non-trivial. Yes. So this guy is projective. This guy is also projective. Yeah. Then we can take the stable category. Then stable category become this we have only 3 incomposable objects. So as I said, they also study the using covering theory. So meaning that let's see how to generate a new page. Yes, good. So we maybe let's look at the graded. So let's do this. That's a Z there. So this is the graded submodule category. So that's similar to above. Then this is the objects is given by this submodule. But in this situation, the Xi is a graded module over the truncated polynomial algebra. So for this example, it's n is equals 2. So then the gradient is given by the degree of t is 1. Then somehow you get a covering of the above quiver. Looks like this. So because you have to consider the gradient in this situation, then the above quiver becomes a infinite one. For example, if we start with k 0 to k, then in base this is still a projective injective object, but this you have to degree shift a. Yes. Then this is there's no change, and this. So we at some place you have to have this degree shift, and for example this is that sequence you have to become so k shift by 1. So that's no then you don't have this identification. So in above you have identification, but here there's no. So we continue. Yes, and also. So this is k shift by 1 and k shift by 1 and so on. So this is a infinite one. And then if you so the above is the projective injective. So if you kill this kill this projective injective, then you got the stable category. So the stable category of this guy. So then kill L, then you see easily that this is the derived category, bounded derived category of the linear quiver of A2. Yes, because we kill all the so this guy is projective, and this guy is also projective injective. So you kill them then, and then you have a covering. So this is a covering to the ungraded submodule. And this phenomena holds at least for if n is at the most 5. So this is so we get nice AR quivers, and sometimes you get some equivalence when we get to study the graded submodule category. So this is fine. So this is one side of the story. Another side of the story is that you consider weighted projective line. So in this situation, we consider this x with 3 weights. So this is a weighted projective line with weight type. Sorry, with type 2, 3, and n. So this is certainly due to Geiger Lenzing. And the Picard group doing the isomorphism class of line boundaries. So this is given by rank 1 abelian group. So this is denoted by L. So this is a abelian group generated by 3 generators. So this is subject to a nice relation. And also this works quite general. So so in so this so we consider the category of weight boundaries on this weighted projective line. So this is the category of weight boundary. And homologically, this category is also very nice because it's quite it's also well known that this category is equivalent to some category of graded co-Markov modules of some Grunstein ring. So this category is Frobenius. So this weight boundary category also quite generally for any weighted projective line. So it's Frobenius with all the projective and injective given by all line boundaries. So in this situation, line boundary are denoted by OL vector. So this L vector is in the Picard group. So and So we have to compare this weighted positive line with the previous submodule category. Yeah, for this you can draw this AI equivalent very explicitly because this guy is domestic, so everything so this is derived to some term algebra. So we can draw this. We only draw a piece, so because this is infinite, so we only draw a piece. Let's see. So this is a line bound. So actually, that's a tilting object in the derived category of weighted positive line. So yeah. So actually, this is E6 tutor, I think. So this is rank 2 bounder, and this so this yes. So this guy is rank 2, rank 2. Yes. So this is the omega, right? Minus omega, I guess. But anyway, this so this again a rank 2 ones. Yes. Yes. Yeah. So this dot is just a line bounders. Yes. So maybe this is OX1. Anyway. So then this is periodic. So this is yeah. So actually this picture I draw this fundamental domain by. So this is the fundamental domain by the shift of this subgroup. So again, you can also take the stable category, and then you kill all the line boundaries. Then in the domain we only left three. So then similar happens in above. So in this situation, the stable category is the same. So you see this object explicitly. So it is the same as the bounded dual category of this A2. Yeah. Yeah. So in this uh, so in this comparison, then we have at least we have a stable equivalence of triangle categories because both are equivalent to the A2 quiver. Yeah. Uh, but notice that when for the unstable ones, so before we take the stable category, so these two categories are not the same because they have different numbers of in some sense different numbers of projective inject objects. Yeah. So for example, in this fundamental domain, you have six, I think six intercomposable projective. In above, there's only two. So we have somehow more. So this guy has more projectives, injectives. So so they are not equivalent before taking the stable categories. So the interesting result, or main result of Kussin Lenzing Meltzer. So they say that there's some kind of Frobenius quotient between this category. Let's take n, any n. So this is Frobenius quotient for any n. Uh, and actually, the kernel of this quotient is can be described with kernels we denote by f. So this the line bond we are given by line bundles. So this f is the so-called fading, meaning they are killed by the functor. Fading line bundle, some line bundles. So this includes to all line bundles. Just remember that all line bundles are projective injectives. So in other words, so this so we take some projective injective, not all, to take this this quotient category. This is becomes a Frobenius. Then this is equivalent to the graded submodule category. So this equivalence really becomes the equivalence of that category. So all the homological structure are encoded in left hand side, also right hand. So yeah, they are compatible with these functors. But these functors are quite mysterious to some extent, and also the choice of this f. I did not write down this. The choice of this f kind of artificial in some sense. So we the maybe I'd like to see. Before say we said the goal, maybe I just remark that also later Kussin Lenzing and Meltzer realized that this might be extended to more general situation. So this vector boundary, say stable category maybe. A, B, N, so A, B can be quite general. So this is also equivalent to some stable equivalent to some graded Z graded so-called two flag category. Two flag. So for this two flag means that this so we have to consider two chains of submodules. So like this, A minus one. So but A1 is equal to B minus one. Then this is also another embedding sequence of embedding one is one B minus two. So you get sorry. So you get two. So you got two sequence of this xi and yj are graded modules. Yes. So this can be generalized. Uh, but here that's a little quite subtle because actually this graded two flag category has many exact structures. So you have to choose very subtly, very choose suitable exact structure such that this becomes a stable equivalence. And then the goal of this work is that to somehow to let denote this functor by KRM, this F. So we a more explicit and also in some sense conceptual description of the function is yeah explicit by not so to some extent maybe yeah. So somehow in this work we achieve this to some extent. I think the a little subtle thing that actually we find somehow the correct exact structure on this two flag category. For this we have to consider quite in the title we have this inflation categories. So the inflation category is nothing but submodule category then generalized to exact category. So let's A assumed to be any Frobenius exact category. So in that category, this submodules have to be replaced by so-called inflations or admissible monomorphisms. So let's take n is at the most at least two. So we consider the so-called inflation category inf n. So this the objects in this category is given by a chain of inflations. So this xi objects in A. So this is the objects in this inf category, and then the morphisms are given by commutative diagram. So that's clear, and then you can see that this category also Frobenius category. And if we take n to be 2, and then we a to just the graded module category over kt to the tth n. So this is our the previous defined category. Yes, yeah. So maybe this n is different from that n. Anyway, so maybe we take not to n or take a. Maybe it's better. Let's take a. So we actually we can repeat this construction somehow. So we first let's see. We take this category of inflations, then we consider inf of this category. Yeah. Then so this is how we denoted by inf. A and B can be symmetric actually. So this inf and B. So this is we call the category of AB inflations. Yeah. So we want to somehow justify this. So why is this is related to the two flag category? Uh, so you can because we just repeated this construction. So you see that the objects in this category are given by are given by some kind of inflation grid. Well, it looks like this x11. So this embedded in this. This is xb comma 1. So this is a sequence of inflations. This vertically is also a sequence of inflations, and then you have this xba and this, and then you have this yeah. So this is a commutative diagram of inflations, but we have to stronger assumption on this, such that every small square, actually bigger square is also, is a small every small square is a pullback. So in other words, actually, the whole diagram is determined completely because we are doing pullback. So it's completely determined by the boundary. Yeah. So x is determined by the boundary. Yes. So this boundary is nothing but the two flag category studied by Kussin, Lenzing and Meltzer. But here, you have to be careful because here the exact structure we want on each component is the exact sequence. So this is so it's better to have this all this grid, not just the boundary. So in this sense, technically this is it's better somehow. And then notation is so this Z graded case A comma B n. So this is by definition just the AB inflations category of the graded modules over KT modulo T to n. Yes. So this is should be the to correspond to the two flag category. Yeah. So the first result is that we have some kind of explicit, yeah, maybe uh, up to something, explicit Frobenius quotient of from this vector boundary categories A comma Bn to this A minus one, B minus one, sorry, this to the n to this graded A minus one, B minus one inflation category. And the kernel is also explicit with kernels. So it's given by the additive closure of these line boundaries. And this line boundaries L is equal to Ix1 plus the 3 or Jx2 vector plus the x3. Yeah, so you can describe this kernel explicitly. So let's show how explicit it is. So this construction is a little bit different from Kussin, Lenzing and Meltzer's construction. So I like to show this. Yes, let's see. Yes. So recall that we would have to define this. I don't give the detailed definition of weighted particular line, but let's see. At least let's S. Sorry, not this curved S. So let's S to be this. Let's to the maybe 2, 3 n case. This is the most. So this by definition is the singularity given by x1, x2, x3. This polynomial algebra modulo 1 relation to 3 plus n. Yes. And this is certainly A graded by means of degree xi x2 xi vector. So then this relation becomes homogeneous. Then this S is the quotient algebra is also graded by L. Then it turns out that this vector boundary category also more generally. So this category is equivalent to the L graded. So this L graded modules, M7 modules over this S. And then we identify these two categories. And then how to construct the Frobenius quotient. So actually this for M modules, I mean this is this is justification. So we for each module M, we visualize M as a diagram. So for this example, the diagram is quite simpler. So we consider so M is also graded. So we consider the yeah, we visualize this M. This is the restricted to submodule, a subgroup generated by this S vector. So this means that we only consider the components which are supported on this subgroup. So this is a graded sub-appealing group. This is one piece. Then we have x1. Then this goes to x1 plus the. So this goes to this supported on this coset. So this is S1. Then we vertically we have x2 plus this is also this is too small, but maybe I sorry, let's take another page to have more space. Yeah, we visualize. Visualize. So we view this M as this M is restricted to the subgroup. So this is x1. M restricted to the this is x2. Yeah, this is another x2. Yeah, sorry. Let's see how to, can we do this?
You have to make sure everything is in the area you
Yeah,
catch it. You have a
maybe I will again. Yeah, so this is the subgroup we want. This is x2. And we don't write x2 backwards because you know that actually we have something here, x1, right? So this, but we omit this. We don't need this. And let's look to the x2 plus so this is a coset. That's another coset, 2x2. Because 3x2 is just belong to this subgroup, the cyclic subgroup. So here we have this x1 plus x2 plus vx3. So this is all vectors. And this is given by the largest one, x1 plus 2x2 plus the subgroup. Anyway, so this M in the whole divided into these 6 pieces. Then each piece are connected by this x1 and x2. So this is given by the action of x2. Yeah. Yes. Then the functor. So we call it double co-kernel. So this functor, the double co-kernel functor. So so actually we have to consider the co-kernel here. Let's see if I can have some color. Yes. So we only consider this part. Yes. So what it means? So actually we this part we denoted by C11. So this is induced by X2 bar the C12. So this is like a monomorphism. So this is belonging to the SZ to the N. So where this CII, this C11 and C12 is given by the co-kernel. So for example, the C11 is the co-kernel kernel of this. So you have x2. So this x2, sorry, this is x2. You have something to this. So we have two morphisms to this corner. Then we take the we plus this we add this two morphisms. Then we take co-kernel. So this is C11, and the C12 is at the another module, this biggest module. Then we take the, sorry, there's something wrong. So the x1. So this x1, this x2. So we okay. Mm, yeah, we see this. Yeah, so we see 1 2 is the corner of this biggest module, this quotient of this guy, and because x1 x2 vanish on this c1 and c11 and c12, so it turns out this c11 and c12 really are modules, are modules over the. So you will see. So this is, you see that this is really a module, graded modules over kx3 modulo x3 to the n. Then we identify x3 with a t with another. So then so it's really we obtain a monomorphism. So this is the what I mean by explicit functor. Yes. Good. So finally, I maybe I explain a little bit what's the meaning of Frobenius quotient. Yeah. So the final section, maybe very briefly. So Frobenius quotient. Uh, so so this definition is inspired by some work Demonet and Iyama. So let A and B Frobenius exact category may be different. So this additive functor. So this is we call by definition call Frobenius quotient. If the following conditions are satisfied, so this F is exact and send projective to projective. So then it induces a triangle functor on the stable category, and the on the stable category is the equivalence. Now finally, then and this B has to be a quotient of A. So this F should be full, dense, and so-called objective, meaning that all morphism that's analyzed by F is factored through some objects analyzed by F. So so in this situation, then this B as the exact category is equivalent to some to the quotient of A by some idea generated by the kernels, the essential kernels of A. Yes. Yeah. So so I think the why this notion is of interest, I think that it's somehow the says that the exact structure of B is given by the induced by somehow the exact structure on A. So this is what I mean by Frobenius quotient. But certainly the Frobenius quotient appears a long time ago. So it's not very new stuff, but really just we formulate this differently. So let's say why this Frobenius quotient is not something very surprising. So we have very old examples. Oh, when should I stop?
Well, you have basically until 3 o'clock. Oh,
Okay,
sorry,
good.
so another 14 minutes. Sorry, yes.
Okay, good. Yes. So let's give examples that showing that the Frobenius quotient is really very classic. Yeah. So this is goes back to Eisenbach. Yes. So let R be a regular local ring, a commuter ring. So this omega is a non-zero element in R, usually in the in the maximum ideal. So then on one hand side we have the category of matrix factorizations. So the object is like this. So this like this. So this P1 and P2 are modules, free modules of R, and the differentials are satisfied the D squared equals to omega. So this is the category of matrix factorization. This is a Frobenius category. On the other hand, we consider the hypersurface. Yeah, this is the MCM modules over the hypersurface is also a Frobenius category. So it turns out this is a Frobenius quotient. And the functor is given sense matrix factorizations to the co-kernel of D. Say, then this co-kernel is a module over the quotient ring is the MCM module. So this is the Frobenius quotient, and also the kernel with the kernel is essentially given by such trivial, let's see, such trivial ones. This identity, this is omega. So this guy is sent to zero, and so meaning that all the morphisms are sent to zero is factored through such objects. Yeah. So this is one example of Frobenius quotient. So this is very classic. And actually, we need a generalized or extended version of this example. Yeah. So this is somehow more recent. This is by Xin and Zhang. Sun and Zhang last year, I think, around this. So they generalize this picture. And so there's other work. I mean, I don't mention, but the people not only consider matrifications, actually they are considered this multifold matrification. So you see that previously in the matrification we only have two components, P0 and P1. Then why not just generalize this? So let's see. So on one hand side we have this n matrifications. So we have the similar picture. So for this, we mean that this n factorizations means that it's given by this. Let us take this to the n minus one. So if n is two, then this is just a matrified, and then there's a backwards. This Pn minus one to this, and all the so then this composition of this NDs are equal to this omega times identity. So this is similar to the previous matrification. So we only generalize this n component. This is on one hand side. This is also a forbidden category, and this side you have to consider the inflation category or submodule category, m minus one. This and the modules are given by a maximum Coulomb module over the quotient. Yes. Again, if n is two, then this is just goes back to previous. Because if n is two, then if n one just nothing. So then it's just in the previous setting of Eisenbach. So the most interesting is n three actually. Yeah. So if n three, then this is the submodule category. So anyway, so that's again a Frobenius quotient. So this is a Frobenius quotient. And also the functor is quite easy. So we consider also take the co-kernel, but this time we take the quotient. So we actually let's see, we kill this P0 something. So we take the quotient of P1 modulo P0, and then we take this guy. Then it turns out this D becomes injective, also again on this quotient module. So then this is a sequence of quotient module. Then it turns out this is a inflation, a sequence of inflations or sequence of inclusions. See, so then the really becomes objects in this right hand side. So this functor is well defined. So also this functor is of Frobenius quotient. Yeah, and so certainly second the functor the example below is generalized the previous one by Eisenbach. Yes, and that's we have a general result. We have a general result. We'll call theorem B. So this is very general. So also it's abstract. So F let F be a Frobenius quotient. So we saw actually the two examples. And n is at the most at least two. Then it says that if we then this F will certainly induce induce the functor between the category of inflations. On one hand, it is inflations of A, and then right hand side is inflation in B. So this certainly is F induce this functor. Yeah. So this for any n, so this is certainly true. And it turns out it's a little bit non-trivial. This is also a Frobenius quotient. Yeah. So this is very good. For the proof, actually, maybe I will say that for the for the for to see that this induced functor is a stable equivalence, that's not so hard. But to see that this for example, you have to verify this is the dense and objective and so on. So this is a little tricky. And then, so we maybe a very short remark say that why this is related, and So let's assume this S to be A, B, and N. This is the homogeneous collinear ring. So so actually we want to study the graded modules over this S, M7 module over this S, and it turns out this, because you remember that we have this relation A to the maybe ignore this minus this x2b plus x3n. So this is some kind of factorization. So it turns out you can see this is so this is equivalent to some matrix factorizations, but of A copies so A can be two or can be any. So this kind of A-fold matrix factorization, but also graded, so with a smaller group. So on the sub-algebra generated by this is polynomial algebra. This omega is given by this two. Yeah, so then we have this A-fold matrixization appears in this picture. And then we use the previous forbidden quotient by Sun and Zhang. So then this goes to the inflation category of A minus 1 of some MSM modules of some quotient rings. Quotient some rings. Yeah, maybe I remove. And then you have to apply this theorem A to this, because we have we have first quotient from the MSM modules to the inflation A minus 1 inflation of something. But this MSM module in the bracket, this category also have some Frobenius quotient to something else. So let's see. So so we have this enterprise, so smaller group of this is somehow the smaller. So this is a one-dimensional singularity. Yeah. And this guy also has some property quotient. I mean, using the same, so we have to inf b minus 1 of some. Actually, this guy is just given by the graded modules over the truncated polynomial algebra. So this is what we want. So then we denote by this f. Then you remember we have this. We from the MSM module of S to the A minus 1 inflation category. But we have to use this. We have to use this f. Then we maybe continue. Yeah, we use f. Then we use A minus 1 f. This is also forbidden quotient, as theorem A shows. Yeah. So then we use theorem A, the general theorem, to have something maybe more yeah, b minus 1 of this graded. Yeah. So this is nothing but our s minus a minus 1 b minus 1 this n. So this arrive this this is the content of the theorem A. Yeah. So maybe some final remarks about so so the stable equivalence. So this is the stable equivalence A, B, and N. So this is the stable equivalence. So N, yes. And then on the left hand side, this A and B and N is symmetric. So they have, I mean, so the equal position. So they are equally. So you can exchange this, and then using this stable equivalence, we can change the positions of A and B and N. For example, we change A and B. Then maybe we change this B and N. For example, so this is also yeah. So this is A and B, right? So this is we change the position A minus 1, M minus 1, Z, and B, right? Yeah. So consequently, we have this. So this is us. Yeah. So, but if you recall what's the content, then these objects are quite different. So this uh, so yes. So this equivalence is related to the so-called Hubble-Stahl symmetry. Yeah, yeah. And it seems that this only happens in the Z-graded situation. So if you the ungraded situation, then this may not exist. And maybe very weak remark is that actually this, as I said, this one-dimensional singularity appears in the proof. So actually, this one-dimensional singularity is also related to the this additive categorization of Grassmannian class algebras. But this relation we do not explore really, but we see that there's some connection between the work by Jensen, Qiang, and Xu. Yeah. So then I think I had a good time to stop here. So thank you very much.
Thank you very much, Xiao-Wu.
Yes, thank you. Yeah, sorry, so I'm not so familiar with this
No,
this pad.
it was great.
Yeah, thank you.
So if you have any question, please just unmute yourself and ask. I see Frank has a question.
Yes.
No, actually, it was just clapping. Sorry. Thanks for your talk.
Okay.
Thank you.
I have a question. So this last functor here,
Yes.
it's the orange one is
Yes.
does it have a kernel, and can you describe it?
Yes, it's like a kernel. Yes. So this functor, this functor. So this functor is given. Its kernel is more or less is given induced. Yeah, it's somehow induced by the kernel of f. So actually, because f, so this f here, this is f. So this f also is quite understandable. So everything is explicit. So then this inf a minus 1 f, the kernel of this guy is also computable. So that composing all these pictures, then all the functor, all the kernels are explicit. So that's why in the theorem A, we can describe the kernels quite concretely. Yeah, because everything is very explicit. Yeah, but maybe a little bit long trivial thing is that we have to show that they are really Frobenius quotient. So that's a little bit tricky. Yes. Yeah. Also, in the original paper by Lenzing, they also spent several pages on this to control this exact structure. So this is a little bit subtle. Yes. Yes. Yeah. Yeah. Thank you.
I was wondering. Thanks for the talk.
Yes. Yes,
so
thank you.
236 is
Yes.
tame, right?
Tubular, maybe. It's better to
Tubular. Yeah. Right.
Yes.
So. Does it have any special features? Because I think
Yes, you're right. Yes, thank you. I mean, this is the work by Klaus Ringel, maybe. Yeah. So here, so in this situation, at least on this Z-grade case, they use the covering. Then you it turns out that this category has many algebra are related to tubular algebra. So then using this fact, then they can classify all objects in this S3, both this category and this category. Yes, and it turns out that the AR quiver has many tubes. So that's why also you can use the result by Kussin Lenzing Meltzer in that weighted projective line case. It's also tubular weighted projective line. So they have this quotient functor. Then in principle, one can say that also you can draw some conclusion about the AR quiver of this category. So it can consist of many tubes indexed by infinite set. So these are related to some. This is related to the slopes of the boundaries. So this is given by many tubes.
Yeah, because I think the 236 example is a Z mod 6 quotient by an elliptic curve, essentially, right?
Yes, you're right. So it's you're right. So so actually that's example curve. It's a elliptic curve plus some finite group action. So that's equivalent.
Okay. Z mod 6.
Yes.
Yeah.
Yes.
Yeah.
Yes.
And so because there are other tubular algebras of that type, but they're like
Yes.
weights 333 or like 244. But do you
Yes.
see a similar story to what you talked about for those other weights, or is it particular
Yes,
to?
so as I said, this let's see, where is it? So this also the already contain observe that this A, B, and N can be any. So for example, as I said, as you said, that we can take the 3 case, but then this side is not a submodule case. So for example, if we consider this 3, I think then this is related to A, yeah, so something like this. So this is the Y2, and then this, yeah. Sorry. So this is Y1, and this all these xi's are graded module over the K to the T3, I think, yes, something like this. So it's and then I suppose. I suppose no one look at this incomposable objects in this two flag categories intensively. So I suppose that something can be done here. So yeah. So
And
this is yes.
and
But I have no idea how to do this.
And the case 2222, so 4 weights, is that?
Oh no, 4 ways is not downloadable because in that
Okay.
state it's not a hypersurface. So yeah.
I
So
see.
this is
Okay.
a very good, also very good problem. So in that case it's a complete section. So I suppose we have to. Yeah, we have to use more complicated things. Yeah, I have no idea. Maybe.
All right, thanks a lot.
Yeah, thank you. Thank you.
Yes. So if there are 3 numbers, just A, B, and then it corresponds to graded 2 flag category. So if there are 4 numbers, for example, 2222, can it correspond to graded 3 flag category?
I don't know. I have to say I don't know. Yeah,
Okay,
because
thank you
in
very much.
that, yeah, because in that case that's not a hypersurface. Then we can't do the like Eisenberg did, yeah, or generalized Eisenberg theorem. So you have to use maybe that's related to some so-called higher matrixization or higher dimensional one. So this is, but that's more very complicated. So.
I see. Thank you very much.
Yeah, thank you. Maybe they're related. So I should think about this. Yeah.
Thank you for the interesting talk. And
Thank you.
classically, the category of matrix factorizations or maximum Cohen-Macaulay modules are also equivalent to the category of singularities.
Yes.
Geometry
Yes,
of
you're right.
And is
Yes.
there an analog for multifold matrix factorizations or inflation category?
Yeah, that's related. Yes, thank you. Thank you. That's also a very good question. So as I said, so we are concentrating on the relation between the n-fold matrifications with the n-1 inflation categories. But so this category is also related to the singularity category of certain graded modules or graded module over some commutative algebra. So that's studied. Thank you. So this is also some work by Demonet. So he also studied this in the commutative algebra side, and they consider some, if I'm not mistaken, some Conora periodicity type theorem concerning this. And that's quite a commutative algebra. So maybe that's related to your question. Yeah.
Yeah,
So I
thank you
should
very
mention.
much.
Yeah. Thank you. Yeah, I should mention this work. Yes. Yeah, maybe I just take this 1 minute say. I also mentioned that this work is also related to maybe just another remark. So actually this consideration is quite general. So we can we can have similar equivalence. So we have a similar equivalence like this. So this is the maximum concurrent modules of the 4 Klein group of let's see, x, y, z times 2x2 2 y2 plus z to the n, say something like this. So here this x, the degree of x is 1, 0. This degree of y is 0, 1. So it turns out this MCM module is equivalent to the graded module over kz module zn. No, this is module k, not the graded module k. So this is module k. Because this degree z is trivial. Degree z is trivial. So this you see that this is some kind of Canora type equivalence. Yeah. So but I also mentioned this. We observe this, but it turns out it's not. So how? What's the precise relation between this guy with Canora type equivalence is not clear. So and the proof of this, because our consideration is quite general, so the proof applied to this situation also even more generally. So during this we find some kind of new phenomena, and this equivalence, yeah. So actually we don't understand this very much. So how to compare this guy with classical canonical periodicity theorem? So it's not clear at all. So for example, here the field K is be arbitrary. So but for classic canonical periodicity, usually the field is characteristic different from 2 usually. So yeah, so that's some subtle things that's not unclear at all at this moment. Yeah, I just mentioned this.